Hello everybody, it seems today is a very special day since nobody is online and offline at the moment. So the lecture is just for record. Okay, that is section 22.1. And it will be term by term integration of functional sequences and series. So the problem is in the possibility to integrate a sequence term by term. And I'll start with an example. And this example is a continuation of an example from the former lecture. So let me recall. I started, I think, with n squared. So we checked during former lecture that the limit is equal to 0 for all x from 0 to 1, but not uniformly. And now look at what happened with integrals. So with integrals of the function itself, we can integrate explicitly, easily. So we make substitution. 1 minus x squared equals to t, so dt equals to 2 minus 2x dx, and it gives equality x dx equals to minus dt over 2, and x equals to 0 will be transformed into t equals to 1, x equals to 1, to t equals to 0. So we integrate by substitution and obtain the following equality. So minus will be compensated by changing the order. So after substitution we have integral from 1 to 0, so we change the order. It compensates minus sign, and we have n squared over 2 integrals from 0 to 1. So x dx is replaced by dt, and we have t to the power n dt, and it gives t to the power n. We know how to integrate it. T to the power n plus 1 over n plus 1, substitution from 0 to 1. It gives n squared over 2 times n plus 1. And we see that this sequence tends to infinity, plus infinity as n goes to infinity. So, but you see that integral of the limit is equal to 0. So if we denote by f of x the limit, then we have that fn of x tends to f of x for all x from 0 to 1 as n tends to infinity, but the integral tends to plus infinity. So it has no finite limit at all, right? But the integral from 0 to 1 f of x dx is 0. Another example says that the integral, so here we had limit of integrals equals to infinity. Finite limit doesn't exist, but if we change a little bit, like it was done also during former lecture, then still limit fn tilde of x equals to 0 for all x, what was considered during former lecture. But now integral from 0 to 1 fn tilde of x dx, as we know, fn tilde is equal to 1 over n integral of fn of x dx. So we have n over 2 times n plus 1, and it tends to 1/2 as n tends to infinity. So now there exists a finite limit of integrals fn of x dx, which is equal to 1/2, but it doesn't equal to the integral of the limit fn tilde f of x dx. Okay. Okay. Next example. Example 2. Consider the following function. So okay, we take cosine of 2 pi m factorial x, yeah, and that is, yeah, and let us take power n, and maybe to avoid cosines, power 2n to avoid problems with minus, and limit as n tends to infinity. Yeah, like that. So let it be fm of x. So let's try to understand what are values of fm of x. So if x can be represented as a rational number where q, okay, let's see, from 1 up to m, yeah, then for sure, Yeah. Then fm of x equals to 1. Why? That is because of, look what happens with m factorial times x. If we multiply m factorial times x, where x is a number of this form, then for sure this denominator q is among multipliers of m factorial, and it means that m factorial x is integer. So if m factorial x is integer, then cosine of 2 pi m factorial x is equal to 1, and the value is equal to 1 to the power 2n is always 1. So that is true. Now, what is about limit as m tends to infinity of fm of x? Obviously, for every x rational, if x is a rational number, then what happens? If x is a rational number, then it has such a form, and for sufficiently large m factorial x will be integer, and it means that all fm for sufficiently large m are equal to 1, hence the limit equals to 1. And what happens for irrational? Okay, in fact, we observe easily that if x is not rational, then for sure fm of x equals to 0. Why? Because m factorial x is for sure not integer, so 2 pi m factorial x is not equal to 2 pi k, hence cosine is strictly less than 1 in modulus, and when we take sufficiently large power, we know that arbitrary number which is less than 1, when we take it at a large power and tends to infinity, so the limit is equal to 0. So you see that every function fm equals to 0 for irrational x. So we have 0 for all x irrational. And we know this is precisely Dirichlet function. Which is not integrable on any interval ab. So you see that fm of x has finitely many, only finitely many discontinuity points. Hence fm are Riemann integrable, and in fact integral fm of x dx equals to 0 for all m. But there exists no integral of the limiting function. So you see that in general, term by term integration of functional sequences is impossible. I gave examples of, so there are several possibilities which are, possibilities from the point of view of pure logic, namely, okay, either there exists no limit of integrals, there exists a limit of integrals which is not equal to the limit of the integral of the limit, and there exists no integral of the limit function at all. Okay, so you see that we have all possibilities. Everything is possible. Okay, now, nevertheless, there is a positive result, so theorem 1, which says that if Fn are Riemann integrable on AB for all and natural, and Fn is sequence converges uniformly to F on AB, then F is Riemann integrable on AB, and limit of the sequence of the integrals exists, and it is equal to the integral of the limiting function. Okay. Proof. First of all, I want to write down definition of uniform convergence. Definition of uniform convergence of Fn. It says that for arbitrary epsilon greater than 0, there exists number n natural such that for all n greater this capital N, and for all x in the interval AB, we have an equality Fn of x minus f of x less than, okay, let it be epsilon over 3 times b minus a. Now, let us fix, so fix n greater this capital N. So we choose epsilon greater 0 arbitrarily, and now we fix n greater than capital N. So what we do, we use Riemann integrable. So Fn is Riemann integrable, and then in fact I use here Darboux integrability, strictly speaking. So more precisely, we use Darboux integrability, but they equal, as we know, Riemann integrability and Darboux. So for this arbitrary epsilon, there exists partition such that we have inequality upper sum minus lower sum is less than epsilon over 3. Okay, now okay. Now let me write down what is upper double sum for Fn. That is, okay, if P is, let it be x0 less x1, so less xm equals to b. So partition P, let it be like that. So what is upper double sum of Fn? By definition, that is the sum of mk times delta xk, where delta xk are lengths of small intervals and capital Mk is supremum of the function f of x for x in the interval xk minus 1 xk. Sorry, Fn here, right? And okay, to indicate n here, I'll put also n here. These are upper double sums. Now, look what we can observe. If we look at the related supremum of the limiting function, then because of definition of the uniform convergence, what we observe? We observe the following. So we observe that the difference between mkn and mk is less or equal than epsilon over 3 times b minus a. Why? Because from the properties of supremums, we can find values of x for example, look, okay, let me give it in full details. So for arbitrary eta greater than 0, right, there exists x in the interval xk minus 1 xk such that mk minus eta less than f of x less or equal than mk. That is by the definition of supremum. By the definition of supremum. Now, as we know from uniform convergence, we deduce that f of x minus fn of x is less than epsilon over 3 times b minus a. Hence, fn of x is less or equal capital Mk plus epsilon over 3 times b minus a, and greater than so fn is sufficiently close to f, so I should subtract here also minus epsilon over 3 times b minus a, right? And what it gives, and as we know, supremum is for sure greater than lower bound here, so we deduce that mkn is greater or equal than mk minus eta minus epsilon over 3 times b minus a. Now look, eta was arbitrary, hence, since eta is arbitrarily small positive number, we deduce that in fact mkn is greater or equal than mk minus epsilon over 3 times b minus a. But we can repeat this consideration starting not from mk, but instead of that we can start from aken n. So we start here with n, additional n, and so we change roles of fn and f, and it gives analogous inequality with mkn minus epsilon over 3 times b minus. So analogous, right? Analogous. Okay, so it gives the desired inequality. So we obtained. Then what happens with, so in particular what follows? What I need from that inequality is that in fact, this inequality is necessary for me. This inequality is necessary for me. So I can write the following chain of inequalities. Upper darbu sum for the function f, which is equal to the sum, k starts from 1 up to mk times delta xk. So by this inequality it is less or equal than the sum k from 1 up to n mkn plus epsilon over 3 times b minus a. delta xk, and that is equal to first terms gives us upper double sum for the function of n, and second terms gives the following sum, which is equal to, this sum is equal to b minus a, so altogether epsilon over 3. So we obtained the inequality. I will write it here: u of pf less or equal u of pfn plus epsilon over 3. Analogously, we can prove that L of pf is greater or equal L of pfn minus epsilon over 3. So you see the difference between u and L the interval with ends at L of pf and u of pf may be enlarged, but it can be enlarged no more than to 2 epsilon over 3. So altogether those inequalities give us the estimate less than epsilon. And it means, since epsilon was taken arbitrarily, it means that we found partitions such that difference between upper and lower Darboux sum is less than epsilon. So it means f is Riemann integrable. Riemann integrable. Okay, so first part is proved. Now let us prove the second part. Okay, so I can erase it. Okay, so let us finish the proof. So now we know that this integral exists, and we need to prove that in fact it is equal to the limit of the sequence of integrals. So let us estimate the difference between those integrals. Okay, we know properties of the integral, so it can be replaced by the integral of the difference. And then modulo of integral is less or equal to integral of modulus. Now look, I can take not all, just first 3 quantifiers from the definition of the uniform convergence. So for arbitrary epsilon, there exists capital N, such that for all n, what can we deduce? Since for arbitrary x, modulo of the difference less than this number, epsilon over 3 times b minus a, so the function under the integral is less or equal epsilon over 3 b minus a. Hence, by properties of the integral, we can put this upper bound inside, and it gives, oh sorry, why I wrote 0, 1, I'm very sorry, from a to b every time. Integration was from a to b, a to b, and finally it gives epsilon over 3 less than epsilon. So what is underlined is precisely this equality by definition. So theorem is proved. And theorem 1 prime is analogous assertion for series. So if Fn are Riemann integrable on AB, and the series Fn of x converges uniformly on AB, then the sum of Fn of x is Riemann integrable on AB, and integral of this sum equals to the sum of integrals from a to b, okay, from a to b. Fn of x dx. The proof is immediate, since we need to consider so theorem 1 prime is immediate corollary of theorem 1. Why? Because we need to consider partial sums Sn of x equal to the sum k from 1 up to n fk of x, and finite sum of Riemann integrable function are Riemann integrable. Hence we apply theorem 1 to the sequence of partial sums, and that's all. We continue. Now section 2. Term by term differentiation. of functional sequences and series. So once again, I'll start with example. This example shows that even uniform convergence is not sufficient to deduce the possibility to differentiate term by term a functional sequence. So, example 1. Consider such a sequence: fn of x equals to sine nx over square root of n. Since modulo fn of x is less or equal 1 over square root of n, and limit 1 over square root of n equals to 0, then fn converges uniformly to identically 0, in fact on everywhere on R. So we have uniform convergence of that sequence of the whole real line. Now look at derivatives. So derivatives are equal to square root of cosine nx. And we see that, okay, if x equals to, let's say, 0, then fn prime at 0 is equal to square root of n, and it tends to infinity, plus infinity as n tends to infinity. So the sequence of derivatives does not converge to the sequence of derivatives of the limit function. So we cannot differentiate term by term functional sequences, even in the case when we know that a sequence converges uniformly. We need to suppose more. So theorem 1 of that section is about term by term differentiation of functional sequences. So suppose that, so we have three suppositions. First, fn are differentiable on, let's say, an interval. Okay, let's say interval AB. Second, there exists a point x0 in AB such that there exists a limit. There exists a limit of the sequence fn at x0. So finitely. And thirdly, the sequence of derivatives fn prime converges uniformly on AB. So we have three suppositions. Then, first, we have three assertions to be proved. First, the sequence of Fn of the functions themselves converge. Oh, sorry, here converge. The sequence converges uniformly on AB to, let's say, f of x. Secondly, f is differentiable on AB. And third, limit of fn prime of x equals to f prime of x for all x in AB. So that is about the possibility to differentiate term by term functional sequences. So proof. Okay, let's start with uniform convergence. So fn prime converges uniformly. Then by Cauchy criterion of the uniform convergence, what we deduce. So for arbitrary epsilon greater than 0, there exists there exists capital N natural, such that for all n greater than this capital N, and for all which letter to use, but let it be psi. In AB, we have inequality fn prime of psi minus f. Oh, sorry. That is Cauchy criterion. I'm sorry, I forget to insert also for all. Okay, let it be in the form for all m greater than n as well. We have for all psi in AB, fn prime and psi minus fm prime psi less than epsilon over 3, I guess. No, I think 3 b minus a. 3 b minus a. I think I need that one. So let it be inequality star. I'll use it later also. And now let us suppose all those quantifiers are the same. So we take arbitrary epsilon greater than 0 and we choose capital N such that for all n and m we have something. Now take arbitrary x and t in AB. Then write down the following difference: fn of x minus fn of t minus fm of x plus fm of t. I'm sorry, I don't need star here. I will need star in another place over there. So let me replace it by using triangle inequality. Not yet triangle inequality. So before triangle inequality, I'll write it is equal to what? We can look at this expression as the difference. Okay, I may even put it from the beginning like that. So you see, that is it was wrong, so let me rewrite it like that. Fn of x minus fm of x, yeah, minus fn of t minus fm of t. Yeah, I need that one. Now look, what is written here? We have difference between values of a function, namely function fn minus fm, and we have difference of values of that function at points x and t of the interval ab. But we know that both functions fn and fm are differentiable on that interval, hence the difference is also differentiable. So we have a function which is differentiable at the closed interval with ends at x and t, and continues in that interval naturally. So we can apply Lagrange mean value theorem. So by Lagrange mean value theorem, there exists psi in between x and t. I will write like that, but maybe t is less than x, so maybe in opposite direction it should be written. So I can write as fn prime at xi minus fm prime at xi times x minus t. That is less or equal modulo fn prime of xi minus fm prime of xi times modulo x minus t. Now I use Cauchy criterion of uniform convergence. So we have less or equal epsilon times modulo x minus t divided by 3 times b minus a, and that is less than epsilon over 3, and this inequality will be star, which I'll use later. Because in fact I'll use not that one but the former. But at the moment I need just the very last inequality. So now what we did use now, look, here x and t were arbitrary points of the interval AB, right? Now, second supposition about convergence of the sequence of fn x naught implies that for arbitrary epsilon greater than 0, okay, I fixed epsilon, so there exists capital N1 such that for all n greater than capital N1 we have an equality, and for all n greater than N1, so I use Cauchy criterion for the sequence fn at x naught. We have an equality fn at x naught minus fn at x naught less than epsilon over 3. So now, for arbitrary n greater than maximum of n and n1, and for arbitrary m greater the same maximum, we have both inequalities, star and the last inequality, and it gives the following. So modulo fn of x minus fm of x, right, like it is written here, it is less or equal, so instead of t I want to take x naught, so we obtain epsilon over 3 plus modulo fn at x naught minus fm at x naught, that is by star, then by form inequality less than 2 epsilon over 3 less than epsilon. And now what is we obtain? For arbitrary epsilon there exists such a natural number such that for all n greater and for all m greater than this number, and for all x in AB we have, so here for all x in AB, yeah, I need it, we have inequality fn of x minus fm of x less than epsilon. So by Cauchy criterion of the uniform convergence, okay, I'll write here implication. So implication by Cauchy criterion of the uniform convergence, we know that fn converges uniformly on AB. So denote f of x, it will be the limit of fn of x. So now we know this sequence converges uniformly, in fact, right? So first claim is proved. Now we need to prove other two claims. So for that reason, consider the following functions. Phi n of x is equal to fn of t minus fn of x over t minus x for t in the interval AB without the point x. And analogously, we define the function phi of x, that is f of t minus f of x over t minus x, where t is in the interval AB minus x. So, sorry. Phi n, let it be of t. Yeah. Those functions depend on t, and x, let x be fixed. So x is arbitrary point of the interval which is fixed. From now on it is fixed. So now we define those functions of the variable t. Now, what happens as t tends to x? As t tends to x, phi n of t, because of differentiability of the function of n, phi n of t converges to the derivative fn prime at x. So we have limits of every function phi n as t tends to x. So next claim is that phi n converges to phi uniformly on, as n tends to infinity, on AB without x. So, for that reason, what we do? I just combine, so take arbitrary epsilon greater than 0. Then there exists capital N, so I'll use inequality star, and better to say I'll use the first part of this inequality. So for arbitrary n greater than capital N, x is fixed, and for arbitrary t in AB without x, so in fact, look, I don't want to prove that phi n converges uniformly to phi, but instead of that, I'll prove that it converges uniformly to something at the moment, right? So phi n converges to something. And for that reason, for arbitrary n, let me insert here for arbitrary m greater than n. And then, what gives star? Let me write down what gives star. So, phi n of t minus phi m of t. So, what is it? That is, I'll substitute f n of t minus f n of x minus f m of t minus f m of x divided by t minus x, right? So, and we recognize immediately the left hand side of inequality star. Now I'll use not the very last, but next before the last inequality in star. So numerator is less or equal epsilon over 3 times modulo t minus x. So we cancel t minus x, so we have epsilon over 3 b minus a. So it means, indeed it means, so by Cauchy criterion, of uniform convergence, it means that phi n converges uniformly on AB minus x. And of course, for arbitrary fixed t, since we know that Fn converges to F, then we obtain that phi n converges to phi. So it converges to phi uniformly. And now, to conclude the proof of the theorem, what we need, so we need to use theorem about uniform convergence and limits. So theorem uniform convergence and limits implies, better to say, what it implies. So we know phi n converges to phi uniformly on AB minus x, and there exists limit as t tends to x, phi n of t, which is equal to Fn prime at x. Hence, we have the limit as t tends to x, phi of t exists, and it is equal to Fn prime of x. And now look at phi of t. So we know there exists a limit as t tends to x of this expression, and it is equal to, oh sorry, I forget to include here limit of Fn prime of x, right? So the existence of this limit says it is equal to f prime at x. It exists, and the limit equals to the limit of the sequence Fn prime. Okay, theorem is proved. And let me write down theorem 1 prime for series, term by term differentiation of series. So if Fn are differentiable on AB, there exists x naught in AB such that the series Fn at x naught converges, and the series of derivatives Fn prime of x converges uniformly on AB, then the series converges uniformly on AB, and the following equality: derivative of the infinite sum of Fn prime equals to the sum of derivatives for all x in AB. So we can differentiate term by term a functional series. When we can differentiate it? When the series of derivatives converges uniformly, and our series should be convergent at least at one point. That is the result. Okay, so this section is over. We have 5 minutes. Okay, next example is not for this section. In fact, next thing which I want to talk about is so-called van der Waarden example. So look, the first example of this section says that even uniform convergence of a series does not guarantee that the resulting function will be differentiable. And it gives a possibility to construct very funny example. And firstly, such an example was constructed by Weierstrass. And it was extremely surprising. So Weierstrass constructed an example of a function. So there exists f, which is continuous everywhere on R, but is differentiable nowhere on R. This example was extremely surprising, and in fact during first years of differential and integral calculus, people thought that mostly functions are differentiable. Okay, of course, everybody knew about, let's say, modulo x, right? Modulo x is not differentiable at a point, but it considered as a very rare story, so people thought that most of functions are differentiable everywhere except for maybe finitely many points. And Weierstrass gave an example which disproved that opinion, and in fact later it turned out that roughly speaking most of functions are like that, and these are very natural examples. But okay, during next lecture I plan to give you another construction of that function, so it will be given as a theorem. And just to finish this lecture, I would say there is very important thing in stochastic processes, so-called Brownian motion, and trajectories of that Brownian motion also, they have for sure such a property. So that is not an exclusion, such a situation. Better to say the exclusion is when functions are differentiable. And okay, let me finish my lecture.